And now we move on to the examples part of our discussion of simple circuits. First, let's have the following problem. In the circuit shown, you are asked to determine the resistances small r and capital R. In the circuit, you have a real EMF source with an EMF of 12 volts, and according to the problem, the terminal voltage is 11 volts. There's a 6 ampere current that's going around the circuit. So according to the problem, we have an EMF of 12 volts, a terminal voltage of 11 volts, and a current of 6 amperes. Since we have a real EMF source, terminal voltage is equal to EMF plus minus IR. If we look at the figure, we see that the 6 ampere current is entering the negative side of the EMF. Therefore, we use a minus sign in the equation. V is equal to EMF minus IR. The only unknown is the small r. Isolating, we are able to calculate the resistance small r to be 0.16666 and so on ohms. With regards to the large resistance capital R, Ohm's law tells us V is equal to IR. The voltage across the resistance is equal to the current passing through the resistance times the resistance. Since the resistance is attached to the real EMF source, the terminal voltage is equal to IR. Knowing the current, the only unknown is capital R, and we are able to calculate capital R to be 1.8333 and so on ohms. So we have internal resistance 0.167 ohms, and capital R resistance is equal to 1.833 ohms. And now on to the next example. You have the following problem. In the circuit shown below, determine the equivalent resistance of the network of resistors as well as the current passing through each resistor. As you can see, there are 6 resistors all in all, 1 current passing through each resistor. Therefore, you are asked to get 6 currents, I1, I2, I3, I4, I5, and I6. As you can see in the circuit, there's only one voltage source, 24 volts. Let that be voltage V. You have 6 resistances. Let R1 be 3 ohms, R2 be 4 ohms, R3 be 8 ohms, and R4 and R5 have the same value, 6 ohms, and the last remaining resistance R6 is 5 ohms. As you can also see in the figure, R2 and R3 are in parallel connection, so we can combine them to form R23, 2.666 and so on ohms. R4 and R5, as you can see, are also in parallel connection, so you can combine them as well to form R45. Thus, we are able to get R45, 3 ohms. With R23 and R45, all the resistances now are in series connection, so we can combine them in series. We are able to get R equivalent, R1 plus R23 plus R45 plus R6. Thus, the R equivalent is calculated to be 13.667 ohms. With R equivalent, the circuit now has only one resistance, one voltage source, one resistance. Ohm's law tells us V is equal to I R equivalent. And we are able to calculate the total current to be 1.7560975561 amperes. If we now go back to just R1, R23, R45, and R6, you have voltage source and four resistances that are connected in series. There's only one current passing through the resistance, total current I. That means R1, R23, R45, and R6, the currents passing through these resistances are all equal to total current I. That means I1 is equal to total current I. The same goes for I6. I1 is equal to I6, therefore is equal to 1.756 amperes. The current passing through R23 is also total current I. That means the voltage across R23 is equal to I R, Ohm's law. V23 is calculated to be 4.68292683 volts. You will recall that resistances in parallel connection have the same voltage. That means V2 and V3 both have the same voltage, and that is equal to V23. V2 is equal to V23, and Ohm's law tells us V2 is equal to I2R2. Thus, we are able to calculate I2 to be 1.171 amperes. Similarly, we are able to calculate I3, 0.585 amperes. We can do the same thing with R45. The current passing through R45 is the total current I. Thus, we are able to get the current across R45. And from there, we are able to get the current I4 and I5 due to R4 and R5 being in parallel connection. And we see that I4 and I5 both have the same value of 0.878 amperes. Next, consider the following problem. Again, you are shown a figure of a circuit. In the given circuit, determine the current passing through each resistor. As you can see in the figure, you are asked to get I1, I2, and I3. We let R1 be 3 ohms, R2 be 6 ohms, and R3 is also 6 ohms. Looking at the figure, we see that there are two junctions in the circuit, but in terms of the currents passing through the junction, the two junctions are similar in that they will give you the same equation if you apply the junction rule. Using either of the two junctions, you are able to get the following equation when you apply the junction rule. I1 is equal to I2 plus I3. Analyzing the loops in the circuit, we see that there are 3 loops in the circuit. For each loop, we use the loop rule of Kirchhoff's rules. In this example, we use a clockwise direction for our loops. Applying loop rule, we get 3 equations. Negative 6 plus I1 plus 2I2 is equal to 0. Negative 4 is equal to I1 plus 2I3 is equal to 0. And 1 minus I2 plus I3 is equal to 0. You have loop 1, loop 2, and loop 3 equations. Having now applied the junction rule and the loop rules, we have one equation from junction rule and three equations from loop rule. So we are able to get four equations all in all in the application of Kirchhoff's rules. The rest of the solution is simply algebra. Using your knowledge of algebra, you have three unknowns, I1, I2, and I3. Three unknowns, four equations, enough equations to determine the unknown values. For example, say we take the equation from loop 2, negative 4I1 plus 2I3 is equal to 0. From junction rule, we know that I1 is equal to I2 plus I3. Putting that into the equation of loop 2, we are able to get the following equation. I2 is equal to 4 minus 3I3. If you now look at the equation of loop 3 and put the equation of I2 into loop 3, 1 minus 4 minus 3I3 plus I3 is equal to 0. The only unknown is I3. We are able to calculate I3 to be 0.75 amperes. And knowing I3, we are able to get I2 1.75 amperes. And finally, knowing I2 and I3, we get I1 2.50 amperes. You will notice that in this problem, we used Kirchhoff's rules to determine the answer, to analyze the circuit. Whereas in the previous example, we used simply Ohm's law and resistors in series, resistors in parallel connection to analyze the circuit. That's because in the previous example, you will notice that there's only one voltage source. Ohm's law and resistors in series, resistors in parallel connection are more than enough to analyze the circuit. But if there are more than one voltage source, like here in this example, wherein you have two voltage sources, it's advisable to use a more powerful analytical tool like Kirchhoff's rules to analyze the circuit. Again, if there's only one voltage source, it's enough to use Ohm's law and resistors in series, resistors in parallel connection. But if you see there's more than two voltage sources, that's an indication that you need to use your Kirchhoff's rules. And finally, we have the last example. You have the following figure. Voltage V and three resistances, 8 ohms, 3 ohms, and 6 ohms. If the 3 ohm resistor is dissipating energy at the rate of 120 watts, determine the voltage V. As you can see, there's only one voltage source, so we don't really have to use Kirchhoff's rules to analyze the problem. Let 8 ohms be R1, 3 ohms be R2, and 6 ohms be R3. The power dissipated by 3 ohms, R2, therefore is P2, 120 watts. You will recall that we have three equations for power dissipated by a resistor. One of them is I squared R. Therefore, P2 is equal to I2 squared R2. Isolating I2, we are able to calculate I2 6.3245532 amperes. And since, as you can see in the figure, all our resistances are in series connection, I2 is our total current. There's only one current passing through resistors in series. Therefore, total current I is equal to I2. If we now get the R equivalent, R equivalent of resistors in series is just R1 plus R2 plus R3. R equivalent is equal to 17 ohms. With R equivalent, you now have only one resistance, one voltage source, V, one resistance R equivalent. Ohm's law tells us V is equal to I R equivalent. Knowing the total current I, we are able to calculate the voltage V, 107.517 volts. And that's it for our discussion on simple circuits. Thank you for watching.